Hey guys, I'm Pat Kelly. Okay, in this problem, there's a lot going on. What basically it comes down to is they gave us these three inequalities, right? And they talk about the area that those inequalities create. I did a quick sketch, okay? But then part A, we're supposed to find the area of that shaded region. Part B, if that region is spun around the x-axis, find the volume. And part C, same region spun around the y-axis this time, again find the volume. Okay. Now you can see that I've actually gotten a head start for us, but you'd have to realize that you're the one that would need to decide in part A. If they want me to find the area, oh, that's just the integral. So I already set it up from 0 to infinity, right, with that function inside of just e to the negative x. What we'll focus on is making sure you can actually evaluate these integrals. Similarly, though, in part B and C, you'd have to decide. They want me to find volume, and it's spun around the x-axis. In this case, that would be the disk method. And I've already gotten into the formula and put in our specifics for the formula. For part C, spun around the y-axis. In this case, shell method. And I've already got the formula for that going for us as well. You might want to review on your own, make sure you know how to set these up for a different problem. Because again, I have a head start for us, but you'd have to decide to get each of these problems started for a different function, different situation. Now let's make sure once it's set up that we do get the right answers for our integrals, okay? Okay, so each of these is an improper integral, new stuff that we've been learning. Let's just make sure that we can evaluate each of these. In this case, it's the infinity, of course, that's the issue, so we'll do our limit as b goes to infinity of this integral 0 to b of e to the minus x dx. Okay, now to evaluate that integral, this one's actually not too bad. I don't know if you've grown to love exponentials yet. They integrate and differentiate so easily. I still have my b to infinity, but then this e to the negative x is just e to the negative x again, but you would have that extra factor of minus 1. And I'm evaluating that from 0 to b. And then we put in our limits of integration, equals limit still, b goes to 0 still, sorry, b goes to infinity still. And then I'd have minus 1 over e to the b. Felt like throwing that negative exponent downstairs. Subtract what happens, so minus a minus though, put a 0 in, e to the 0 power of course is just 1. We're almost done actually, because now we get to do the limit. As b goes to infinity, this denominator goes to infinity, which means the overall fraction goes to 0, and all you're left with is the 1. So our answer for that area equals 1. Onward. Second problem, the volume. As I mentioned, we have our disk method set up and ready to go. So what it's going to come down to is evaluating this improper integral. Again, I'm going to have that limit as b goes to infinity. I do have a pi in front. Never want to lose our coefficients out front. b goes to infinity. And this is another integral. It's not too bad to do. I think I'm actually just going to go ahead and do it. E to the negative 2x will show up again, e to the negative 2x, after we anti-differentiate. And that factor of a minus 1/2 would come in from like a u substitution if you had done it in an exponent. So we're really just looking at that as our antiderivative and evaluating from 0 to b. I'm replacing the infinity with a b. Okay? And so this equals the pi out in front, and now my limit as b goes to infinity, I'll put in that upper limit, minus 1 over the 2, e raised to a minus 2b, sorry, positive 2b because I'm taking the negative exponent and putting it downstairs. Subtract what happens, so now it's a minus becomes plus, and I'm putting in that lower limit of 0, so minus or plus 1/2, And then e to the 0 power again becomes 1, right? And so we get that. Okay, now I'm going to do my limit. As b goes to infinity, here again, that's your denominator going to infinity, so the fraction goes to 0. I'm looking at a plus 1/2 inside my limit. Don't forget the pi out front. And looks like this one's going to equal a pi over 2 for that volume. Okay, last one. They saved the best for last for us here, I think. Again, here's our formula from the shell method, but as soon as I get into this one, a little bit of work on this one. I've got my 2 pi out in front, and my limit in order to address the indefinite integral as b goes to infinity. And I've got the integral from 0 to b x e to the minus x dx. And not as easy as the last couple of integrals that we just did, because in order to tackle that guy, I'm actually going to do some integration by parts. So I'll go off to the side here, and I've got to do a u equals and a dv equals. I'm going to let my u equal just x, and my dv equal that e to the minus x dx. And then du just equals dx. My v will equal e to the minus x with that extra factor of a minus 1. Okay, take those pieces, put it into your integration by parts work. I'll slide over here, try to continue the equals, and I still have my 2 pi out in front. I still have this overall thing inside of a limit as b goes to infinity. And now let's do our u and v, which is minus x, e to the minus x. And the catch here is that's evaluated from those limits of integration, 0 to b. But I'm still not done with the integration by parts formula. It's supposed to be minus the integral of v du. So I'm trying to put together my v du. There's a minus there, so that'll make this a plus. The integral of e to the minus x dx. This integral still has the limits from 0 to b. Right? In order to keep organized here, if I can, everything inside the square braces is resulting from our integration by parts work and is all still inside my limit that I'll have to do here. Before I'm ready for my limit, let's actually do this integral. That one's not too bad. Equals 2 pi still. Limit as b goes to 0, b goes to infinity, and now I still have this minus x, e to the minus x. I know I have my limits of integration written down there, but I'm going to go ahead and evaluate this integral. E to the minus x would be e to the minus x, and I would have that factor of a minus, so that just creates a subtraction right there. And so those limits of integration apply to all of this now then, 0 to b. And then square braces again if it helps, because that's all still inside your limit. Now I'll do my fundamental theorem of calculus, plugging in your limits of integration. This equals the 2 pi still. The limit as b goes to infinity still. And I'm going to put a b in here and get minus b e to the minus b, subtract e to the minus b, and then subtract what happens when I put a 0 in. This 0 would just make that 0, that term 0, put 0, and then minus e to the 0 power is 1. So we're almost done, but there's still a little bit of a hiccup, because when I go to do this limit right there in the first term is another indeterminate form. Okay, so I've got to address that. Let's see if I can do that over here, where if I'm just looking at the limit as b goes to infinity, I'm only worried about that first term. Let's write that as a minus b in the numerator and an e to the positive b in the denominator, so that L'Hopital is ready to go. I'll do a L'Hopital step now, which is just the derivative of the top, derivative of the bottom. Derivative of the top is just minus 1. Bottom is e to the b. Okay, now you can do this limit, and you can see that if the denominator is e to an infinity power, denominator becomes huge. That goes to 0. And that tells me right there that that part's going to be a 0. And so I'll try to go down on my last line here and see if we can get a final answer. 2 pi. We know that I'm doing my limit now, so I won't write LIM. That goes to 0. Minus, putting an infinity in here, this e to a negative b power, if it helps, think of it as 1 over e to the positive b power, because that's actually, again, going to be a 0. Okay? And then minus a minus 1 plus 1. Oh my goodness, I think we've got it. 2 pi. Final answer for that volume. Good work on that one, too. Okay. Go take a day off. You deserve it.